Hi, my name is Chris Seaton. I'm a senior staff engineer at Shopify, and I'm going to talk about understanding Java programs using graphs. So here's where I'm coming from with this talk. I've got a PhD in programming languages, but I've got a personal interest in languages beyond that. One of the great things about working in programming languages is that you can have a conversation with almost anybody in the tech community. So almost anyone who uses programming languages has opinions on languages, has things they wish were better in languages, things they wish were faster in programming languages. So a great thing about working in languages is you can always have a conversation with people and you can always understand what they want out of their languages, and you can think about how you could provide that as someone who worked on the implementation of languages, which I think is a really great thing about working in this field. I'm formerly from the Oracle Labs VM research group, part of the Graal team. Graal is a new just-in-time compiler for Java that aims to be really high performance and give many more options for how we optimize and compile our applications. I worked there for many years, but I've currently moved to Shopify to do compiler research on the Ruby programming language. So I work on Ruby, but I work within a Java context because I'm using Java to implement Ruby. And that's the Trough Ruby project. So Trough Ruby is a Ruby interpreter working on the JVM. Not to be confused with JRuby, which is another existing implementation of Ruby on the JVM. And what I'm trying to do is apply Java compilation technology to make Ruby faster, to make Ruby developers happier. So we use the same kind of technology in Java, but applying it to Ruby. What's this talk about? This talk is about understanding what your Java program really means. So we can read our Java source code and we can have a model for how a Java program works in our heads. We can use, if we wanted, the Java specification to get a really deep understanding of its semantics and what it really means. But I think it's good to understand how the JIT compiler, so the just-in-time compiler, understands your Java program as well. So it's got a slightly different model of the program. We can reveal that by using some internals of the compiler, and we can see how the compiler understands your Java program. And I think that can help us better understand what our Java programs are doing if we're at the level where we're trying to look at performance in detail. We'll be thinking in more depth than bytecode. So if you've heard of bytecode, we'll be starting there, but not quite as much depth as machine code. So I'm aiming to keep this all accessible. So we'll be using diagrams to understand what the compiler is doing rather than using dry text representations of that. So it should help it be accessible even if you're not sure what goes on beyond bytecode. This talk is about knowing rather than guessing. So I see a lot of people argue about what Java does and the performance of Java and what's fast and what isn't and what Java can optimize and what it can't. But I often see people guessing online and trying to guess what Java does. This talk is about knowing what Java does and how we can use some tools to really understand how it's understanding your Java program and how it's optimizing them rather than guessing about what you've read online. It's about testing rather than hoping for the best. So we can use some of the techniques I'm going to talk about in this talk to test the performance of Java applications. Again, rather than simply relying on what you think it should do, we can test how it should optimize. And all of that is in order to get the performance we want. So we're talking about contexts where we want high performance out of our Java applications, and how do we do that and how do we test it. But the rest of this talk is live, so we'll move to a live demonstration. Okay, now I've got a slightly clackety keyboard. I hope that's not too distracting. Sorry about that. So the first thing I've done is I went to graalvm.org and I downloaded the GraalVM, which is the distribution of Java we're going to use to do these experiments. So you can go to the download link and you can download the community edition for free. It's GPL licensed, so it's easy to use. So Graal means a lot of different things, unfortunately. It can be a little bit confusing and different people use it to mean slightly different things. Sometimes people can sort of talk past each other. So essentially Graal is a compiler for Java that's written in Java. And by that I mean it produces machine code from Java bytecode. So I'm not talking about a compiler from Java source code to Java bytecode. It can be used as a just-in-time compiler for Java within the JVM. So replacing something that is called Opto or C2 within the hotspot JVM. So it replaces that top-tier compiler with a different JIT compiler. But it can also be used to ahead of time compile Java code to a native image, so a standalone executable which runs as if it's being compiled from C or C++ or something like that. That has no requirement on a JVM. It can also be used to compile other languages via a framework called Truffle, and this is what Trough Ruby does. It compiles Ruby code to source code via Java using Graal as a just-in-time compiler. The reason it can do all these different things is because it's essentially a library for compilation, and you can use that library in many different ways. You can use it to build a just-in-time compiler, or you can use it to build an ahead-of-time compiler, and you could do other things with it as well. So it's a library which you can use different things. That's why it's one term that's used for doing so many different types of things. That's packaged up as something called the GraalVM. The GraalVM is a JVM with the Graal compiler and with truffle functionality within it. So that's what the GraalVM means. You may hear the term GraalVM compiler. That's the same as Graal compiler. I took GraalVM and I've put it onto my path. So I'm going to do path equals GraalVM contents home bin path, and that gives me Java on my command line path. Now I've got an example Java program here that has a simple class. It has a main method which simply runs a loop, and it calls this method called test, and what test does is simply adds together two parameters and returns the result, and it's kept as a static to keep it nice and simple. The way I've set this up is with this loop, the purpose of that is to cause this method to be just-in-time compiled. I use just an endless loop because I want the compilation to happen naturally. I don't want to force the compilation in any unusual way. And the input to the method are two random variables. So I have a random source, and the random variables go into the test routine. The reason I do that is because I want the program to not be static at compilation time. So I want real dynamic data flowing through it. So the just-in-time compiler can't cleverly optimize anything away because actually it's static. Now we've got Java C, which is our Java compiler, on our command line from GraalVM as normal. So we can do Java C test .java like that, and that converts our Java program to bytecode as you'd normally do. So we have the source code now, which is how we'd normally understand the program as a human being. So we can read that and we can reason about it. But there's more ways than that to understand your Java program. Now the first one you may be aware of is an abstract syntax tree. You may know this term from an undergraduate compiler class if you've done that sort of education. But what it is a representation that Java C uses to understand your program. So I'm using a plugin here for IntelliJ that allows you to see how the Java C compiler understands your program. So you can take an example source file like the one we have here, and you can use this pass button, which gives us an option to inspect, and then we can see how the Java C compiler understands our source code. So we have here a class, which is our test class, and it tells us what comprises that. And then with that we have a method declaration, which is our add declaration. You can see it highlights the source code which corresponds to it, and it has private, static, has a name, it has a return type, and within that it has a block which is the body, has a return statement, and then it has the binary operator, and within that we can see it has X and Y as two inputs. This is the abstract syntax tree, or the AST, which is the simplest representation the machine can use to understand your Java source code. Now we already said we compiled to Java bytecode, so that means there's another representation we can use to understand our Java source code. So I'm going to use Java P. So Java P, and I think the command is C on test. This will disassemble our Java bytecode from the class file. So it'll give us the, I need to have, it's because it's static, isn't it? So I need to do, excuse me, P. Great, sorry, yeah, you need to use P to get extra members. So what we have here is a representation of that adding routine test as written as the Java bytecode. So we had the AST, which is how Java C understands it. It produced this bytecode, which is what goes into the class file. So we have, it loads an integer, loads another integer, so 0 and 1 correspond to the two parameters. It adds them as integers, and then it returns an integer. So that's what it does. Load them, add them, and return them out. So nice and simple Java bytecode there. Now, when you run this Java program at runtime within Hotspot with the just-in-time compiler enabled, it converts it to machine code. And we can see the output of that machine code using some special flags. So what I'm going to do here is use this set of flags here. What all these flags mean isn't particularly important. If you look up on some blog posts, you can quickly see how to get machine code out. But I'm going to simply run one of these. And this tells us the machine code that the Java just-in-time compiler has produced from our Java code. So it tells us it's compiling the find the method we're after. Test, there we go. So this is the test method. And this is the machine code it's produced that actually runs on your processor. So there is a add operation in here, and that is the actual add, which corresponds to the add we wrote in Java, but it's buried around some other stuff. Now there's quite a bit of golf here. We talked about the AST and then the bytecode. Now we've jumped all the way to this low level, hard to understand machine code, which we can't really use to understand our Java program. It's far too dense. This is a tiny method, and there's already quite a lot going on there. So in this talk, what I want to do is address that sort of gulf between the Java bytecode and the Java machine code. Now there's a couple of tools we can use to do this that exist already. One of them is called JitWatch. So I'm running JitWatch here as an application in the background. It's a tool, and what you can do is you can use basically this flag called log compilation. I'm going to run our test program with that. And it runs as before, but now it's producing an extra file of output which we can interrogate to understand a bit more about what the JIT has done. So I'm going to open the log that we just produced, and I will analyze it. And there's our class, and it tells us there's a method in there which is just-in-time compiled. And this tool is a bit better than the Java P command line tool and the print disassembly we used, in that now it gives us all those together. So it tells us the source code, the bytecode, and the machine code output. So this add operation corresponds to this add operation in the bytecode, and then we said that this was where the actual add was, and yet we can see it's connected up, and it tells us that's the actual add operation going together. So this is a bit better, and it shows us how these things link up, but there's still somewhat of a gulf here in that how's it getting from this bytecode to this machine code, and that's what we're going to answer using the next tool. So I'm going to use some more flags now. I'm going to add something called graal.dump. And what this does is it asks the Graal JIT compiler to print out the data structures it uses to understand the compilation. So the program runs as normal. After a while, I'll cancel it, and then we get an extra directory, which is this Graal dumps, which lists all the compilations which the JIT compiler has done. Now I'm going to use a tool here called Seaton, which is a command line tool for reading out these graphs. So we've got a directory, so I'm going to run Seaton, and I've got a directory of these Graal dumps, and I'm looking for hotspot compilation, and these are all the things hotspot has compiled, and we're looking for test, so 172. I'm going to ask it to list all the things it compiled within when it was compiling that method. This list is hard to understand, but these are all the phases the compiler runs, but I'm going to simply jump in and get it to look at after passing. So what does the code look like after it's been passed? I'm going to say I want you to render this. So this is what Seaton does. This prints out a compiler graph, and this is the central idea of what this talk is about. So this is a graph. It's a data structure. It has edges or arrows, lines, and it has boxes, nodes, vertices. It's a flowchart effectively. So it tells us how the just-in-time compiler is understanding your Java program. So what we have here in the center is an add operation, which is that add operation in our method, the key thing. And what this graph is telling us is that there's input flowing from the 0th parameter, so the first parameter, and the first parameter, so the second parameter, which flow into that add operation as x and y. And then the add operation goes to be returned as the result. There's also a node which says where the method starts and where it ends, and they simply are connected by one straight line. So there's no control flow going on. The green arrows represent data flowing, and the red arrows, which we'll see more of later, the thicker arrows, they represent the control flowing through the program. And the green or the oval boxes represent data sources, and the green or diamond boxes represent operations on data, and the red or rectangular boxes represent some sort of decision or some sort of control flow being made. So you can see that this adds operations that goes together. How can we use this to understand some Java programs? And what can we use this to understand about how Java understands your Java programs? Well, let's look at an example. We've got this add routine here. I'm going to expand it to have another parameter. So x, y, and z. And what I'm going to do is I'm going to introduce the extra variable here. Like that. So x plus y plus z. And then I'm going to run the program again. So I have to compile it because I've modified it, and then run it as before. One, 7, 3. So now we've got two add operations. You can see that the result of the first add operation flows into the input to the second operation. So this is x plus y plus z, the third parameter. Now Java's got local variables. What do local variables mean to how the just-in-time compiler understands it? Does it make a difference to your program when you use local variables to change how your program works? I've seen some people argue online that using local variables is slower than just using code directly with an expression because they think the compiler has to set a local variable somewhere. Let's look at what that actually looks like. So I'm going to modify this code now to do int a equals x plus y, and then do a plus z. So we've got different Java source code now, but that achieves the same thing. Let's look at what the compiler understands that. So I compile again, run again. Uh, 175. Oh, that's not right. Oh, sorry, that's because I have done that. So we introduced a local variable, but you can't see any difference in the resulting graph. So the result of this is x plus y. That's now assigned to the local variable a, but that local variable doesn't appear in the graph. It's like the just-in-time compiler's forgotten about it entirely. What this edge is here that represents is the data flowing from the add operation from x plus y into the input that adds it to z. Now it doesn't matter if that value is calculated and stored in a local variable, or if it was simply passed with an expression. All the compiler cares about is where the data is flowing. And there is a local variable here between node 5 and 6, but the compiler doesn't care about that. It can ignore that and just know that this is where the data comes from, this is where the data is going. So we can see we get exactly the same graph out of the program if we use local variables, or if we don't. It doesn't make a difference to how the just-in-time compiler optimizes it. And this is what I mean by we can use this tool to understand how the just-in-time compiler understands our program, because we can change things in the program and we can see what differences that actually makes to the just-in-time compiler and why. So far our graphs have been pretty simple. I'm going to introduce some control flow now, so some if statements, things like that. So I've got an example already set up. So example if. So now I've got this method example if. It has a condition, an x and y, and if the condition is true, it sets a to be x, otherwise it sets a to be y, and then it returns whatever one of those it was. We also have something in the middle which sets an int field to be the value we're setting it to. The reason we do that is to put a point in the program where there's some sort of action taken, so we can see that action more easily in the graph. Otherwise sometimes the graphs get very compact very quickly and it's hard to see what you're looking for. So I'll run this program. I'll remove the Graal dumps, I think. So example if 182. So what we have now is a graph that includes control flow. So before, the only red things, the only rectangular things were start and end, but they come in now when we have a control flow, such as a loop or an if. So now we have is the first parameter, so our condition, is it equal to 0? 0 meaning false. If it is equal to false, then we use x, otherwise we use y. And we can see us assigning x to that field here. And then we can see the result comes from either x or y, depending on which way we took the if. So what this is a special node called a fi node that says take which value we want based on where we control flow diverged. So we can see our control flow now has a verge in it where it can go one of either way, just like our program. We can see now that the red or the thick arrows have a meaning for control flow. Now we can use this example to see a really interesting point about how Java optimizes your program. What I'm going to do is I'm going to change this random boolean that says whether we want to take the first branch or second branch, and I'm going to give it a constant value. So I'm going to change it from random to being always being false. So this condition is always false now, so we're only ever going to use this branch. What do you think this is going to do to the way the Java compiler, just-in-time compiler, understands your program? We see this pattern quite often in things like logging, for example. You may have a logging flag which is off most of the time, or sometimes it's on, sometimes it's off. And does that add some sort of overhead to the way your program is compiled? Let's try it out. Uh, 180. Right, we've now no longer got any control flow in our graph, but we had control flow in our source code, so where's it gone? What the compiler says is it has never seen that value be anything apart from false. So it's gone ahead and it's just in time compiled your program, assuming it's always going to be false. Now, because that value is coming in dynamically, it could change. So what it's done is instead of an if node, it's now got something called a guard node, which is saying, I want you to check that that the first parameter is still false. So first parameter equals false, check that's true, but then it carries on assuming it's true. So we have the store field and it returns simply the first parameter. If it wasn't true, so if it wasn't true that the value is false, then it does something called de-optimizing, where it jumps out of this compiled code and goes back into the interpreter. But what we can see here is that the just-in-time compiler looks and profiles what values you have flowing through your program and uses those to change how the program is being optimized. The benefit of this is there's less code here now because there's only one of the branches are compiled, but also it's straight line code. Right? This guard is written in such a way that the processor will know it's not likely to fail, and therefore it can go ahead and do this code afterwards while that guard is still being checked. So here we can see the profiling going on and working in action. I'll give you a more advanced example now of what we can see about what the just-in-time compiler is doing by using an example which looks at locks. So I'm going to take an example here. I'm going to take the code which calls this. We don't need that anymore. So what we have here now is a method called example double synchronize. It takes an object and an X. Sorry, did need the field still, and then it synchronizes an object once, writes a field, and then it synchronizes on the object again and writes a field. Now, why would you write code that synchronized on an object twice back to back like this? Well, you probably wouldn't, but you may get this code after other optimizations. So if you call two synchronized methods, then you're effectively doing this if you call them back to back. Or if you have code that's inlined other code that uses synchronized locks, you may get them back to back like this. So you may not write this manually, but it's the sort of thing you may get out automatically from the compiler. And the driving code uses the same object for each lock, but it allocates it new each time, then it just passes in a random integer. So let's compile this. I'll remove the Graal dumps first. One 175. Okay, and what we can see is what we'd expect to start with. We have straight line code. Those kind of synchronized blocks, the object that's used in them is called the monitor of the object. And we take that object in as the first parameter and we enter the monitor of the object and then we leave it, and in between we write the field, and then we enter it again, write the field and leave it. So this is, we can see here that we're locking the same object twice, which is wasteful. What I'm going to do now is look at a later phase of that same method being optimized. So I'm going to use the list thing, which gives me all the phases which are being done. I'm going to grep for lock elimination. So we've got two phases here, before lock elimination phase and after lock elimination phase. So it is 57 and 58. So I'm going to render the graph again at stage of compilation 57. What's happened here is the program has already been optimized a bit. So some things have already been changed, and it's also been lowered to a certain extent. So some higher level things are being written as lower level things. So for example, there's implicitly, we can't synchronize on that object if it's null. So a null check has been inserted and made explicit here. But we still have the monitor enter, the write the field, the monitor exit, the monitor enter, write the field, and the monitor exit. What I'm going to do now though is look at the same graph after something called the lock elimination phase has run. So this is a compiler phase within Java's just-in-time compiler, which is designed to improve our utility of locks. So this is at stage 58 now. So I'm going to look at just after the next phase, and we can see what has gone on here. What's happened is we now have just one monitor enter, we write both fields, and then one monitor exit. So we can see what's going on here is it's seen the two logs are back to each other, next to each other, back to back, and it has said I might as well combine them into one single log, and I might as well lock just once, do both things inside the block, and then release the log. So this is an optimization that you may have been aware was going on, you may not be aware it was going on, but instead of debating whether Java is able to do this for our code or not, we can look at the graph and find out. And we can either do this as a manual process, as I've done here. So I said for this example code, I want to know if the two locks are synchronized or not. So I wanted to know if effectively I was going to get this code out, which is what we have done. I can test that. But because we're using command line tools and we're using these files that come out of the compiler, what we can do is we can also write a test to do this. So I work in my day job at Shopify on a system called Truffle Ruby. So Truffle Ruby is a Ruby interpreter, so it's an interpreter for the Ruby programming language. It's written in Java and it runs on the JVM as a normal Java application if you want to. It doesn't require any special functionality inherently. But it uses the Truffle language implementation framework. So this is a framework for implementing programming languages produced by Oracle Labs, and it can use the Graal compiler to just-in-time your interpreted language to machine code somewhat automatically. So it uses a technique called partial evaluation. Instead of emitting bytecode at runtime and compiling that as if it came from Java, what it does is it takes your Java interpreter, applies a mathematical transformation to it with your program, and produces machine code from that. It's capable of some really extraordinary optimizations thanks to Graal. It can inline very deep. It can constant fold through lots of meta programming, things like that, which is essential for optimizing the Ruby programming language, which is very dynamic. So this is how we actually test Truffle Ruby at Shopify. The optimizations that we care about having been applied are very important to us because of they're very significant for our workloads. We have tests that those optimizations have applied properly, and what they effectively do is they automatically look at the graphs as I'm doing here, but they do it using a program, and they check that the graph looks as I expect. So here you could query this graph and you could say I expect to only see one monitor enter and one monitor exit. The other thing about Java that people don't always know as well when they're trying to understand and guess at what it would do is, of course, Java is open source. The compilers are open source. You can just go and look at how they work. So we can see here that this lock elimination phase has worked really well for us and has done what we'd expect. If you go to Graal on GitHub, you can look at how these work. So we said it was the lock elimination phase that did what we wanted. And we have a test for it. Here you go, lock elimination phase. And this is the optimization which applied what we wanted. Great thing about Graal is because it's written in Java, you can jump in and it's very readable. I'm not pretending that anyone can do compiler stuff, anyone can work on compilers, but I think anyone can read this code who's familiar with Java and Java performance work and can understand what's going on here. So this is a full production optimization phase here, and we're saying for every monitor exit node in the graph, so get all the monitor exit nodes in the graph, look at the next node. If the next node is another enter, and if the two locks are compatible, so they're the same object, then replace the exit with the next enter, and that's what it's done to our graph to be able to optimize it. There was a exit here and it said replace it with the node that comes the next node after the next enter, which was this right here. So I think I'll summarize by saying that the point of all this is that we can get the compiler's representation for how it understands our programs out of the compiler, and we can use that to gain a better understanding of what Java is doing with our programs ourselves. And that means that you don't have to guess at how your Java program is being optimized. You don't have to rely on working through the spec. You don't have to rely on hearsay that you see online about what Java might do or might not do. You can check it yourself and you can see what it's doing. And I think it's relatively accessible via these graphs because you're looking at a visual representation, not having to pour through a log. You can simply see how it's transformed your program and understand what it's doing. And because of these logs are files that we can get out of the compiler, we can also use them to test stuff. So we can build tests by saying, does the graph look like how we expect? Has it been compiled how we expect? So I think this is some more options for understanding Java and for understanding how our Java code has been optimized, checking that it's been optimized as we expect, which makes it easier, I think, to get the performance we want out of our Java applications. I'll give you some resources. A lot of the work here on how to understand these graphs come from a blog post, Understanding Basic Graal Graphs. If you look at that one, that will give you a way to understand all the concepts you might see in a graph. So what kind of edges you see, what kind of nodes you see, what normal language concepts compile to. You can get Graal from graalvm.org. You can get the Ruby implementation from there as well. The tool I'm using to look at graphs is something produced by Shopify called Seaton. I also demonstrated JitWatch and the Java parser, which allows us to look at the Java ASTs. And finally, I'm on Twitter at ChrisGSeaton, always looking to be engaged about Java and Ruby performance stuff. Thank you very much.
So I've got to say that was a very interesting presentation.
Thanks.
I'm not trying to sound surprised, but I'm a big fan of understanding more about what JIT does. So it's very interesting to see what you're doing with the idea of the graphs, and then getting the JIT watch to expand out the information.
Yeah, I think a lot of people spend their time guessing at what Java does, and there's a lot of myth and misinformation and old information there, and we can just check, right? So I see people having arguments online. Java does this, Java does that. Well, let's just go and take a look, and you can find out for real, and you can find out for real whether it's working on your code. And you can even write automated tests to figure out what it's doing for real by looking at these graphs.
Yes, because as you say, if you put a local variable in, does it actually really get produced as a local variable? And I assume, because I'm just kind of chatting here because I don't see that there's any actual questions on the Q&A thing, so I'm going to kind of riff a few questions myself. Is that like escape analysis? So because you're not actually using that variable outside of the method, or the result outside of the method, that it can is it related to escape analysis, or is that just simply
no, it happens in a different phase. So what it does is it says every value that's produced in the program, so every expression that is in the source program produces is given a number, and what it says is every time you refer to that expression, it just uses the same number. It's called global value numbering. So if an expression's gone through a local variable, it still has the same number as if you wrote it there directly. So to the compiler, it's exactly the same thing. And this is why if you write A plus B twice independently, they're the same expression. So the compiler says, well, I'll give them the same number. And then they'll be used, used once. So again, people might use a local variable and think, I've got A plus B twice here, I'll put it in a local variable and use it. Does that make it faster? No, it doesn't, because it's exactly the same thing. There's still readability reasons, and it's important to say that making your code readable is a separate concern, and that's a very human thing. But it's important to understand how the compiler actually understands your code and what it actually does with it.
Okay, yes, because I remember from my days many years ago doing C programming, and do you make a variable a register? And what impact that has on whether it improves the performance or not.
Yeah, and it's kind of historic, and it doesn't really mean anything anymore.
Yeah, because then they ended up with, this is after my time, but they ended up with register. It's like, what? Okay, good. I'm still not seeing any questions on the actual Q&A chat bit. The other thing I really liked you were explaining about was how the code can be optimized based on previous profiling. And so I talk a lot about that with the stuff I do, or what we do, as speculative optimizations, which I guess is the same approach as what you were describing there.
Yeah, and again, these graphs allow you to see what's happening there, and what are the properties you can find on the graph, because there's more information in the graphs than is visible, because the tool I use tries to show enough stuff to be reasonably useful without putting an avalanche of data. So one of the things it can do is it can tell you the probabilities. So you look at the graph and you can see which path is more likely to be taken than the other. So you can see whether a path is never taken, or it's always taken, or whether it is taken 25% of the time, or something like that. You can use that information to understand your program again. And the compiler uses that in different ways. People often think it only uses it for binary reasons. So it says if a branch hasn't been taken, then compile it. If it's never been taken, don't. So you may wonder, why does it collect more profiling information than that? Why does it collect fine-grained information? Because it actually has a float for the probability, so quite a lot of precision. The reason for that is the register allocator. It will try and keep registers alive for longer on the more common paths than the less common paths.
Yes, of course, that makes a lot of sense.
Yes, it's worth gathering that kind of more detailed information, and you can start to do. Obviously, these are like last 1% optimizations rather than the most important things in the world.
Yeah, because I mean that's the thing I always find interesting, because a lot of people, because obviously you worked on the Graal project, and so Graal has become very popular recently because of the idea of native images and ahead of time compilation. And I get that that's very good from the point of view of startup time. So you're immediately running native code, so you don't have the warm up. But if the JIT compilation, because you can do things like speculative optimizations, I mean, you can do profile guided optimizations with Graal, but you can do proper speculative optimizations, and as you said, de-optimize if need be. You can get that slightly higher level of performance through JIT compilation or optimization.
Yeah, and again, graphs are great for seeing this. We should do a blog post on this. Like why is JIT faster than AOT? Because if we can use the same tool can be used for native image. So if you want to understand how your native image programs are being compiled, you can dump out graphs in a similar way. If you look at the C-frame repository, there's commands for using native image as well. And if we look at some example realistic Java code, we'll be able to see, well, the native image graph is actually more complicated. Why is that? Oh, it's because the JIT was able to cut this off. No, this wasn't needed. Get rid of that, and so on, and get to be simpler code. So because it's the same tool, it works for both. You could look at them side by side and see where the native image is having to do more stuff to keep it going. But yeah, that's a common misconception that native image will always be faster. I think it may be in some cases faster peak performance.
Yeah, I mean, definitely.
In the future, it may get better, but yeah, you're right. It's a startup and a boot warm-up sort of tool.
Yes. Great. Well, still not seeing any questions in the Q&A section, so I think based on that we'll probably kind of wrap things up here, because like I say, I mean, that's fascinating presentation. I really enjoyed that. Great stuff.
Thanks. Great. Thank you very much, Simon.
Okay, thanks a lot. Bye.